So I just got finished teaching my first STEM camp.
How did it go?
I think it went pretty well. Learned some good things. Did some cool stuff. So yeah, I think it went pretty well. Let's see, how do I... And all right, so we finished up chapter 13 last time, right?
Yeah, we were on chapter 14.
We started chapter 14.
We don't know if we heat transfer.
So now we're on conduction, right?
Yep. This one has formulas, or is it just kind of learning?
Yeah, there are formulas here.
Awesome.
Should be. So essentially what's going to happen for the next 3 sections here is we're just going to learn the formulas that are involved with conduction and convection, well, just conduction really, and radiation. Convection, there are no formulas that are simple to be used there. Convection heating is a very complex process because it involves movements of fluids, which is a very complex process itself. But conduction is pretty much about contact and materials. So here they show a picture of a wall full of insulation. It's exactly the kind of thing I'm thinking about these days as I'm building onto my house. But this is kind of, this is a good little diagram of how this works. Cassidy, are you seeing my computer?
Oh. Well, my phone is logged out for some reason.
Let me see if I can find, let me see, let's see.
That's weird. Hold on.
Join, schedule, share screen. Share screen, share screen. How do I do this?
Yeah, I don't see it.
I don't either, but I can't figure out why I can't see it. There we go, share screen. There we go.
Yep.
All right, there we go. So, this is a nice little diagram of heat conduction, how it happens. On the one side you have a hot material, the other side you have a cold material, and the boundary in between them where they're touching. And the particles in the hot material are moving faster than the particles in the cold material. And those hot particles, as they come to the boundary, the surface here, they collide with some of the cold ones and speed them up. And so it's through a direct contact, collision really is what's going on. The hotter ones speed up the colder ones, and then that relates to a heat transfer. So it's really a mechanical kinetic energy transfer is all it is. And these transfers are almost perfectly elastic in many cases. So the transfer is just a transfer of kinetic energy, which results in higher temperature for the cold one and a lower temperature for the hot one. Because the hot one, as it hits the cold one, gets slower. It gets slowed down by the colder ones. So it's kind of interesting. The heat flow, of course, naturally goes from the hot side to the cold side. That's a spontaneous heat flow that you see quite a bit in nature. You could also think of it as an amount of energy, heat energy Q, passing from a material temperature T2 to a material temperature T1 through a particular distance and through a particular area. Now, if you think of it that way, then you can start to build an equation that relates these things, and this is what we call the heat transfer rate equation, or just the transfer rate equation. And it is the heat divided by time, so it's kind of like a velocity for heat energy. Heat over time is equal to K times A, where K is a constant, again, we use K a lot. And this, in this case, it is the thermal conductivity, I believe, yeah, right there. Thermal conductivity of the material. So every material has a particular thermal conductivity, which tells you how easily heat moves through that material. High heat conductivity materials, heat moves easier. Lower heat conductivity materials, heat moves has more difficulty moving through. And then the area, of course, is the area that is in contact, or the area through which this heat is passing. Temperature change, T2 minus temperature 1, and you divide by the distance that the heat has to travel to go from the one object to the other object. So, here's an example. Styrofoam box has a total area of 0.950 meters squared. The walls have a thickness of 2.5 centimeters. That's your D. Your area, of course, is the 0.950 meters squared. Your distance D is 2.5 centimeters. You're going to want to convert everything into the same units. The box contains ice, water, and canned beverages at 0 degrees. So you know the T cold, right? The cold temperature. The inside of the box is kept cold by melting ice. How much ice melts in one day if the box is kept in the trunk of a car at 35 degrees Celsius? So they just keep adding ice to it as it melts, and keeping it in the trunk, which has a 35 degrees Celsius. So what we're doing here is we're using this equation. We have a temperature 2, a temperature 1. We have a distance, that's the thickness of the styrofoam container. We have the cross-sectional area, which is the area of the container. We can look up the thermal conductivity, and we also know that it's going to be kept in the car for 1 day. I assume we're going to call that 24 hours. Let's see. Their time is equal to 1 day, 24 hours, right? So our time is 24 hours, and what we're going to get, what we're going to solve for in this is the heat. Let's see how much ice melts in 1 day. Yeah, so we're going to solve for the heat. Once we know how much heat was transferred in that 1 day in this situation, then we can set that amount of heat, or we can divide that amount of heat by the amount of heat required to melt a certain amount of ice and figure out how much ice we've melted. So we use essentially the specific heat, not the specific heat, but the latent heat of fusion of ice. So we can figure it out that way. So anyway, let's go ahead and do it. So here we have all of our knowns. They wrote them all down and converted everything for us. That's great. Then they plug them into this equation, and they solve for Q, right? Once you've solved for Q, you have 1.15 times 10 to the 6 joules of energy that was expended that day by heat transferring from outside the styrofoam box to inside the styrofoam box, trying to melt this ice that's inside of there. Then the latent heat of fusion equation says that Q equals M times LF, where we're going to use latent heat of fusion for ice, for solid water. And then the mass is the thing that we're trying to solve for, how much ice actually melts. So we solve for the M, it's equals Q over LF. The Q is the same Q that we solved for right here, the amount of heat that gets into that box, divided by the latent heat of fusion, and you get 3.44 kilograms of ice. So, what thermal conductivities are there out there? Silver, high thermal conductivity. Copper, high thermal conductivity. Gold, pretty high. Aluminum, about half as much as silver. Steel, iron, about half as much as aluminum, a little less than that actually. Stainless steel, very little. Does it surprise you that when you buy pans with steel handles on them for your kitchen, they're usually stainless steel handles? It's not just because they don't rust, it's also because they don't transfer the heat very easily. If you don't use stainless steel handles, your handles will get hot. In fact, most of the time, the pans have stainless steel handles that are hollow so that they can be surrounded by air on all sides and stay even cooler. Very, very common for kitchen appliances.
Would it kind of be like how cast iron, some steel that's mainly iron, can get really, really hot when you're trying to cook with it?
That's right. So cast iron conducts this a lot better than stainless steel. And so a cast iron pot, you don't want to pick up by the handle. I put one of those oven mittens around it when I'm using it just so I remember not to touch it because it can get really hot. It's good to have a pot that can distribute the heat well. To have a pot that has good thermal conductivity is great because then the heat travels through the pot and heats all sides of the pot. And in certain dishes, you really want it to be heated from all sides. Some you don't. For example, if you're making a paella, you don't want that, so you want a pan that's made of steel that's not going to transfer the heat very well and stays cooler on the sides and hotter on the bottom where the fire is. Because then it gets crispy on the bottom and gets that great flavor.
Or if you're trying to put a sear on something.
Yeah, if you're trying to just sear something, you may not even have sides to your pan, right? You might just have a griddle, and you just want it to be hot on the bottom. You don't really want to worry about steaks, for example, are usually just cooked on the top and bottom. They don't want to put anything on the side. That actually creates, if you cook the sides too much, it actually makes it a little too tough and a little too cooked. So yeah, certainly. But you can see here that glass has a pretty low thermal conductivity. Concrete and brick, about the same. Usually your concrete brick is much thicker than your glass, so that helps concrete brick to block more heat, or block heat better. Water, even lower. Fatty tissue without blood, so fat's a good insulator. Everybody knows that, right? Asbestos, plasterboard, better than fat. Wood, even better. That's why we make our houses out of wood. Snow's a really good insulator. Did you know that?
Mm-hmm.
You can make a snow cave and survive in it very comfortably. I've done it. Cork, glass wool, which is fiberglass, right? Wool itself, all very good. These are all things that are used in housing insulation. Glass wool, wool, down feathers are not used in houses very much, but they're used in sleeping bags and coats quite a bit. I have a down sleeping bag, a couple down coats. Very, very warm. Air is almost as good as down. Why? Because that's what makes down a great insulator. It just traps a whole bunch of air.
But then
right?
Air would be slightly better than that.
Air is slightly better than down.
Oh, you said it backward. You said,
So
Oh, did I say it's almost as good as
yeah, I
down?
was like looking, I was like, wait.
It's about the same as down, actually, yeah. So it actually, air itself, as long as the air doesn't move, because if the air moves, all of a sudden you have convection. It can carry the heat from one side to the other. But if the air doesn't move, it's fine. Our house back in Price was made of two walls separated by a gap of air that didn't move. It had an inside wall and an outside wall made of brick. Well, I think one was made of block and one was made of brick. But then there was an air gap in between, and it had great insulation. And that's not an uncommon building method even out here in North Platte. There's quite a few houses made of brick that way, where there's an inner wall and an outer wall and an air gap in between. Great insulation. However, styrofoam is slightly better. Styrofoam not only has air in it as a good insulator, but the foam itself is a very good insulator. So styrofoam is great for that.
So the lower your rate of thermal conductivity doesn't conduct heat through it. So like if you're inside a styrofoam pot or something, all of the heat that you're producing just kind of stays in there.
That's correct. You know, something that's very well insulated can work against you as well. So if you have something very warm inside of styrofoam, it traps all that heat. In fact, it's a great cooking method. It's used all the time. You cook something, and then you wrap it up and put it inside of a cooler. Close it up, and it continues to cook it as it traps that heat. And it's a great cooking method. So let's calculate the temperature difference when you have conduction through an aluminum pan. You have water boiling. It's placed in an electrical element on a stove. Saucepan bottom is 0.8 centimeters thick. It's 14 centimeters diameter, so that'll tell us our distance that we have to travel through the bottom of the pan, and the centimeters in diameter will tell us the area of the bottom of the pan touching the stove element. And the boiling water is evaporating at the rate of 1 gram per second, so that's telling us something about the heat. We can calculate how much heat is required to evaporate water, because that's the latent heat of evaporation, vaporization. We want to know the temperature difference across the bottom of the pan. We're doing this problem the same way. We're going to start off with our equation for the heat transfer rate, but this time instead of solving for the heat, we're going to solve for the temperature difference. We know the heat transfer rate, or we know something about it, and we know the distance, we know the areas, and we know the thermal conductivity of aluminum, so we can plug a bunch of stuff in here. However, we're going to have to calculate the Q from our latent heat of vaporization for that water. How much water is being evaporated? Well, up here it says 1 gram per second. So if it's happening at 1 gram per second, then we want to know, we want to first know how much heat is required to vaporize 1 gram of water, and then divide that by 1 second to get our Q over T. So we do that, we have our mass times the latent heat of vaporization. We know our mass. We don't know our mass. We're going to, well, we do. We're going to do it for 1 gram. So it's 1 times 10 to the minus 3 kilograms, which is 1 gram. And then we're going to multiply by the latent heat of vaporization for water, 2,256 times 10 to the 3 joules per kilogram. We've got all the correct units. We find that it's 2,256 joules of energy needed to vaporize 1 gram of water. And if we do that in a second, then we divide that by a second and we get watts, 2.26 kilowatts, it turns out to be. And then we can go back and plug in this number, 2.26 kilowatts, or 2,256 joules per second, in for this whole thing, Q over T, right here. Once we plug that in for Q over T, we have our distance divided by our K times our area, and that equals 5.33 degrees Celsius for that temperature change when you are boiling water at that rate. So another equation involving Q. Don't stretch, you're making me sleepy. This is a sleepy afternoon. It's been a long day. And then convection. So, like I said before, we're not going to really get into the equations of convection, but let's talk a little bit about, well, they do one thing here. Two things, actually. That's okay. But I would like to talk first about kind of how this how this convection thing can be beneficial. So in a house, most houses are heated at least partially by convection. And the way that's done is that they put the heat source, either your heater or your gas or your fireplace or your whatever, they put that on a low part of the house, the bottom of the house. Why would they do that?
It's where the cold air is.
Because that's where the cold air is that you want to warm up. The warm air is floated to the top of the house due to Archimedes' principle, and the cold air is sunk to the bottom. So we make that cold air hot, and it rises to the top again, and it displaces air that's maybe not quite as hot as it is. And that not quite as hot air goes back down and eventually gets cooler and falls to the ground and begins to heat again, and so on and so forth. And you get this convection current going. That's what they call this loop, a convection current. Up as it gets hot, down as it cools off, back to the heater, up as it heats up, down as it cools off. And while it may not be the most efficient method of heating houses, it does work quite well. But the same thing happens in the pot of boiling water, as we discussed. You have the hot water at the bottom of the pot, and it starts to rise to the top. The stuff at the top sinks to the bottom. You get this rolling effect, like the rolling boil that you see as it starts to boil pretty rapidly. Now let's talk about the convection of air through the walls of a house, because houses are not really airtight. They're not really designed to be. It's not really all that great for your house to be perfectly airtight, because the air would get stale. You would have a buildup of CO2 in your house. You would get sleepy. In fact, there was this funny high school experiment done. This high school kid took a CO2 detector to church with him, and he measured the amount of CO2 in the church, in the chapel, while the sermon was giving his speech, while the pastor was giving his sermon. Sorry, and then he was counting how many people were asleep every 5 minutes, and he was recording the CO2 at the same time. And what he discovered is that people don't necessarily fall asleep just because of the pastor's speech or his oratory or whatever. They actually might be falling asleep because the carbon dioxide in the room is rising as the people are breathing more and more of the air. There's not enough circulation in church buildings. And that's true. Most church buildings, they close the doors when the sermon's going on. And so the CO2 levels rise, and you have less oxygen in your blood, you have less energy, and you start to get sleepy. Kind of funny, don't you think?
So it's not my fault when I fall asleep. in
That's
church.
right. It's not your fault, and you shouldn't feel guilty for falling asleep during the sermon. You should just, that's what I tell my wife every week, because I fall asleep almost every week in church. I deny it,
It's inevitable. that
resting my
you
eyes.
fall asleep in church because of the carbon
That's
dioxide.
right. It can't be helped. It is a physical thing. It's physics. Anyway. So anyway, in this particular case, we have the air leaving the house, and this moderately sized house has these dimensions. This particular volume we'll be able to calculate. And they're saying all that air is replaced in 30 minutes. So that'll tell us how much air is leaving the house per second if we calculate the volume and divide it by the number of seconds in 30 minutes. So we're going to do that. We calculate the mass of the air by the density times the volume here. We get 836 kilograms of air in your house. Bet you didn't realize your house had that much air. Mine has more since mine is bigger than that by far. Well, maybe not by far, but it is bigger than that. But you're losing nearly a metric ton of air out of your house, and it's getting replaced every 30 minutes. Apparently. So calculate the heat transferred from this change in air temperature is our second part. The heat change is going to be the mass of the air that's lost, right, times the specific heat of air times the temperature change. In this case, temperature change is going to cool by 10 degrees Celsius because the incoming air is colder by 10 degrees Celsius, so that's our delta T. Calculate that in Q and you get 8.36 times 10 to the 6 joules, or 8 million joules. And then to calculate the heat transfer time, or heat transfer rate, you take that divided by the time, the 30 minutes, and you get 4.64 kilowatts of heat leaving your house, which means you're going to have to put, if you use electric heaters, you're going to have to use 4.64 kilowatts of electricity to heat up the house, to keep it warm. If you're using gas heaters, you're going to have to use quite a bit more energy than that, 3 times that amount of energy. But gas is cheaper, so most people do that. Now, why is there such a thing as wind chill? Because what?
Because the wind's energy is being used for movement versus.
That's right. When you're just standing out there and the air's not moving, you're mostly losing heat due to some conduction with the air. And conduction with a gas is not much if it's not moving. And then you have some radiative heat coming off your body. But when the wind comes by, all that air that your skin is warming up around you gets blown away and replaced with cold air. And then gets blown away and replaced with cold air. And gets blown away and replaced with cold air. So it's convection. You're actually experiencing convective cooling. So the wind chill factor has to do with a couple of different things. It has to do a little bit with the humidity outside. The drier the air, the less wind chill factor there is. The more humid the air, the more wind chill factor there is. And that's because your body, when it's more humid outside, will have sweat on it. It'll be more moist on the outside, on your skin. And that moistness carries the heat better. So the heat from your body will go out to the edge of your skin and sit in that liquid on the edge of your skin. That's sweat, or body oils, or whatever you want to call it. Doesn't sound good either way, I guess. But then as the air comes by, it will pull off more energy per second. So wind chill factor, very important in places like Nebraska where you get a lot of humidity. Even in the winter, Nebraska is much more humid on the coldest day in Nebraska than on the warmest day in places like Utah. And Utah is just dry as a bone all the time. If you've never lived in a place like Utah or Arizona, you may not ever know or experience this. But it is so dry, it is painful and uncomfortable. But the good side is they don't have a wind chill factor very often. So,
I was in Utah last summer in 2016. It wasn't too bad. It was in June.
where were you?
Salt Lake City.
Yeah, Salt Lake in June is not bad, but Salt Lake is also next to a huge Salt Lake. So Salt Lake of all the cities in Utah is one of the best ones for humidity. It has a slightly higher humidity, but it's still much lower than Nebraska. You know, it's still much, much lower. But it does have a huge lake next to it. I mean, people talk about Lake McConaughey being big. The Salt Lake is much bigger, much bigger. You cannot see across the Salt Lake in any direction if you're in the middle of it. What's that?
Lake McConaughey probably has more water.
Definitely has more fresh water in it. I don't know if it has more water, but it may. It depends on the year. Salt Lake can have a lot of water in it, but it's never very fresh. So
Definition is a Salt Lake.
that's correct. You should see the salt facilities they have. They're huge mountains of salt. Morton has a big plant there, for example. Just mountains 1,000 feet high of salt. It's incredible. Just makes you want to. And then the salt flats are really cool. We took our kids and let them run on the salt flats last year.
You just run and run.
We didn't run, but we kind of walked up to the edge and we're looking around at it. Or all these little bugs buzzing around.
Oh yeah, there's bugs everywhere out there.
It's the perfect place to do, perspective photos. You mess with perspective by making
Yeah.
people look small, making people look small.
Yeah.
Just because you can't tell the difference for eternity. Just
Yeah,
looks small.
that really plays tricks on your eyes out there. So here's an interesting thing. Fur and hair actually keeps you warm by convection. Did you know this?
I do not. I do not.
And this is also why having a down jacket on or a down sleeping bag keeps you warm. The part that is near you is warmed by your body, and it creates these little convection currents. That warm air inside the feathers or whatever starts to travel outward and travel upward, and then it cools and then it falls back down, and it gets warmed again. But that air that stays inside of the sleeping bag or stays inside of your jacket never gets as cold as the air out around the jacket. So it creates this barrier of warmer air, which is extremely nice, right? However, there's added interesting factors. For example, polar bears. They have fur, right? What color is a polar bear fur?
Clear.
It's clear. Okay, most people assume it's white, but you guys have obviously done your homework over your lifetime. It's actually clear. Do you know what the shape it is?
It's like a tube.
Yeah, it's like straws. It actually is. They're little tiny tubes of clear, like polymer, like plastic. And the sunlight, as it comes down, it gets caught in those tubes and bounces down in it like an optical fiber. And that light goes all the way down to their skin, which is what color?
Black.
Black, which absorbs all that energy and turns it into infrared. And then the convection currents are really good in polar bear fur. Okay, it really helps them to survive in the Arctic.
So that means maybe coat with that polar bear fur?
Polar bear fur makes a great coat if you're up there. In fact, it's used by many, many indigenous people out there. However, if you're not indigenous, don't try it because you'll be arrested.
They're about the only ones who could get away with it.
Yeah, I'm not sure they even can get away with it now, but they probably still can. Anyway, let's calculate the flow of mass during convection. Sweat, heat transfer away from the body as you sweat. So Q over T again is going to equal, and this time we're talking about sweating. So when you're sweating, you've got this liquid on your skin that evaporates because of the heat that it's absorbing from the sun or from the air around you. Now you would think that if your sweat is absorbing heat, it would actually heat you up, but it doesn't because it evaporates and leaves your body. So it does get hotter, but it leaves your body immediately, and so you actually get cooler. The hottest part on your body jumps off and goes away. Evaporative cooling. So we have heat per time is equal to latent heat of vaporization per time, right, times mass. So then we use the mass of the water that we lose, which says right here, they're producing heat at the rate of 120 watts when at rest. At what rate should the water evaporate to get rid of all this energy? So we want to know the rate in mass per time. So we're looking for m over t. So this has to be, where the amount of heat that we're producing is 120 watts or 120 joules per second. If we want to calculate mass per time, we take that 120 joules and we divide by this LV. So we divide by the LV and we get, in the end, which latent heat of vaporization for water, and I don't know if they use water or salt water. But anyway, latent heat of vaporization of water, and you get 0.0494 grams per second. So people that say, I'm going to sweat it off, 5/100ths of a gram per second. Remember, a gram is not that much water. It's going to take a long time to sweat something off. You're much better just exercising. People say, I'm going to go into the sauna and sweat off some fat. No, you're much better off going to the treadmill and using some energy. Sweat does not really take that much energy out of your system. You might lose 180 grams per day, though, or per hour. It's still not very much. Cumulus clouds, we're used to these, right? Caused by convection, right? You have this cold front and this warm front, and they collide together. What happens? Where does the cold front go? Down. Where does the hot front go? Up, right? Convection. It's kind of a forced convection thing, and that upward motion causes that warm, moist air to cool off very quickly, and then it turns into little water droplets in the air and creates this huge towering clouds, which then, of course, cool off to the point that they try to fall down again. And they fall down in the form of all kinds of messy stuff. This can also create so much friction between the clouds as they move around that you can build up electricity in those clouds, have lightning strike, and so on and so forth.
Random question, Mr. Daly. I'm assuming these are proper, say for direct solar viewing.
Yes,
That'd
ma'am.
be why I can't see anything else through them, right?
That's correct.
Cool.
Okay, so let's talk about, did we give you any homework from this section? Not yet?
Not yet.
Okay, so let's talk about homework from this section.
From this section specifically?
Yes. Okay, let's do the last problem. A glass coffee pot with the circular bottom. So that's the problem you're going to do, the very last problem in this section.
And this is in the convection one?
Yep. Did we do one for conduction?
No, we haven't done any from any of the other ones.
Okay, let's go back to conduction really quick and get the homework for the conduction section. Okay, let's do the firewalker. So the firewalker problem. The firewalker runs across a bed of hot coals without sustaining burns. Do that one.
Is this 14.1?
14 point.
14.5?
14.5 is the conduction one.
Mr. Daly,
Yep.
I don't think we have anything to calculate that one. We don't have a formula that calculates something crazy.
Turns out it's not as crazy as you think. You can actually hold a hot coal in your hand, believe it or not.
Wow.
One that's turned white and is ready for cooking food.
Wow. Well, you can hold it, you're going to burn, obviously. But
No, you won't necessarily, because the ash on the outside of the coal has an extremely low heat conductivity.
okay.
So it doesn't conduct heat by conduction very well. Coals do not heat your food by conduction, they heat by,
Convection.
they do heat by convection, but also by radiation, mostly by radiation, in fact. So unless you put the lid on top of your barbecue, you're cooking by radiation. If you put the lid on, then you're cooking by convection as well. So, but it's mostly by radiation. Which is where we're going next.
So those are the only three problems. Do you want us to do all four parts of, or all three parts of the Firewalker?
Firewalker and Tether?
The Firewalker and the,
Last coffee pot.
yeah, the pot.
Coffee cup.
The last
On the
coffee pot.
Firewalker one has three parts. Do you want us to
Yes,
do
all three parts. Now, radiation, right? So, we talked about the electromagnetic waves and the curve and everything already. I actually have a demonstrator for this. We could probably do it outside though. Putting ice on two kinds of pavement and watching one melt faster than the other, the darker pavement, which has absorbed more of the radiation from the sun and reflected less of it, so it gets hotter.
Just do
Yep.
or something like you use for water. I forgot to bring my water
Yeah, you can have one of these cups.
bottle. Awesome.
In fact, you can have some Sprite or Coca-Cola. If you
No, I already drank one of my Mountain Dews. I'd probably better not. Well,
want. Okay. Yeah, there's water right there, and if you want this, you can have this.
I might.
Okay. Sorry, we're just providing some liquid refreshment here, Cassie. Okay, so anyway, with radiation, it's important to know how much something is going to absorb or reflect something. And we have an equation for that. We don't try to justify where it came from. But it is called the Stefan-Boltzmann law of radiation. And it tells you how much heat is absorbed in an amount of time, so Q over T, depending on the area of the object, the temperature of the object to the fourth power, something we call the emissivity of the object, E, this little E here, and then the Stefan-Boltzmann constant, which is this constant right here. And that is technically, I think technically they call that a sigma, but I'm not sure. But anyway, it's that constant is 5.67 times 10 to the minus 8 joules per second meter squared Kelvin to the fourth. That's a funky unit system, but that's what makes it work. So, what is this emissivity constant? That other constant, this Stefan-Boltzmann constant, is just the constant that makes this equation work. But the emissivity is actually has to do with the type of material that is absorbing the energy. And everything has an emissivity that can be measured. So something that has an emissivity of 1 is going to pretty much absorb everything that you throw at it. We call that a black body radiator or a black body absorber. And the perfect black body, you will never see anything reflect off it. It will be jet black, and light that hits it will just get absorbed by it. It won't have any kind of reflection off of it at all.
Well, black hole count as that, or is that just because of the gravity?
The black hole is a little bit different, but technically, yes, it does have an emissivity of 1. A perfect reflector that reflects all of the light that hits it is an emissivity of 0, and everything else is somewhere in between, right?
So all the numbers between 0 and 1?
Yes, emissivity E can only happen between 0 and 1. And carbon black, which is the toner inside of a laser printer, is the material that has the greatest known emissivity made by man, 0.99 emissivity.
What's the greatest one in nature? Would that be black
Probably the
hole?
black hole. Technically, it's not a material, so that's kind of hard to classify, but it does. So anyway, it does have to have the fourth power, and that temperature always has to be in Kelvin. It's an absolute temperature. And here you can see the mapping of the radiative heat of a house. The darker red, the more red colors are going to be more heat transfer, and the bluer the colors, the less heat transfer. So yellow is closer to red, get a lot of heat transfer between these windows. Get a lot of heat transfer right here between the floors, lots around the frames of the windows. That's where you almost always lose a lot of heat, is around the frames of the windows. Also the windows themselves, you lose a fair amount of heat. Down here by the foundation, not much. Yes.
I just thought that my dad uses a party, and I could probably get us an infrared camera, like a professional one.
Well, that'd be fun. If you want to bring it in tomorrow, that'd be cool. I actually have an infrared camera I made.
Oh,
I took apart an old camera, an old digital camera, and I took all the filters off of the chip. Because normally they have filters that block ultraviolet and block the infrared. So I took those filters off and I replaced them with a filter that blocks the visible light, which is like these eclipse glasses filter. And then I was able to, then when I take pictures of things that are hot, I just see the infrared image that's coming through. So it's kind of a cool homemade, it's a fun homemade project. If you have an old digital camera you want to play with, the instructions are online. You can make your own infrared camera. It won't work like night vision necessarily, although it does a little bit. It just doesn't work great. But if you have an infrared, if you add an infrared light to it instead of its flash, for example, because I did that with the flash as well. I covered the flash with the filters. Then you can take pictures in a dark place and nobody will know you're taking pictures because they can't see the light. But when you're done, you have all these pictures and they look funky because it shows the skin and the hair differently because they reflect infrared light differently than they reflect visible light. So it's a fun project.
So with the night vision, like, you know, the type you always see in like movies where it's like
Yep.
you see everything almost as a shade of green or something?
Yeah,
Is
so
that using infrared or?
no, not usually. Sometimes it's using a combination of infrared and visible light, but mostly it's just enhanced. What they're doing is they're doing low light, so they're over processing the light that is there. They just have a very sensitive chip in their camera, so it really senses ambient light really well, usually. But sometimes it's also infrared and ultraviolet as well.
So that would be like why in movies if you see like somebody, the good guys have their night vision goggles on and somebody turns the light off and it really hurts because it overloads or something.
Yeah, it does. But also, most of the time, those things are protected against that, so that the night vision goggles turn off if that happens. But it can still cause a problem. But a better pair of night vision goggles actually has its own light source. So the best way to have night vision, especially up close, is to have a pair of goggles or something that is an infrared camera and showing you an image in the infrared, but you also have lights that are infrared shining outward, lighting up everything. But nobody can see those lights because they're infrared, and that's how my camera works. I also built an infrared flashlight, so I could turn on my flashlight in a dark room and nobody could see it. But if I'm looking through my camera, I can see everything in the room. It's really kind of cool. And that's how, like, have you seen the infrared, have you seen the night security cameras? They're surrounded by LEDs on the outside. Those are all infrared LEDs. They just light up the night with infrared light. So if you pass in front of it, take a great picture. So, that's right. So, Stefan Boltzmann law. Here's the Stefan Boltzmann law of radiation, but if you have a change in temperature of something, you can use this version of it here and get you can get the amount of heat transfer.
So this one calculates
From-
the change in heat?
Well, it calculates how much heat is transferred from one thing to another when it's radiative exchange.
So what is the first one?
So essentially what you've got is you've got one object that is one temperature surrounded by an environment of another temperature. Temperature 1 is the object, temperature 2 is its surroundings. And this equation then will tell you how the rate of energy being transferred either from the object or to the object because of that temperature difference in radiation. So let's take a look at an example to help us understand this. Here we have an unclothed person standing in a dark room. The ambient temperature is 22 degrees Celsius in the room, but the person's skin temperature is 33. So the person is temperature 1, 33 degrees Celsius. The room surrounding the person is 22 degrees Celsius, temperature 2. and the surface area of the person is 1.5 meters squared, their emissivity is 0.97. Does that surprise you? What did we say had an emissivity of 1?
Black hole.
Black coal. But a human has an emissivity of 0.97. They didn't necessarily mention that this person is really dark skinned or anything, but this is true. Human beings have a fairly high emissivity, even the Earth. The Earth itself has a higher emissivity, I think, than humans do. Maybe not, but it's in the 90%. It's 0.9 something. So even things that don't look black are actually are pretty good black bodies. They have a pretty good, pretty high emissivity. So it's kind of interesting. So anyway, we take the two temperatures in Kelvin, convert them to Kelvin, put them in the equation, raise them to the fourth power, taking the difference, throw in the area, throw in the emissivity, the Stefan-Boltzmann constant, calculate Q over T, in this case, negative 99 watts. That means the energy is leaving the person because we calculated the person as temperature 1. Right? So the energy is leaving the person and going into their environment at 99 watts or 99 joules per second. And this is one of the reasons that people wear clothes. It is. It insulates us. We do not have fur on our bodies, not much anyway. But there's just, there's a lot of heat loss when you radiate. This is another, how many of you have been camping a lot? How many of you are Boy Scouts or Girl Scouts or 4-H or anything like that?
I think I'm a Boy Scout.
How many of you have seen an emergency blanket? What's it look like?
Thin and silver.
It's a foil bag, right? It looks like a wrapper for a burrito or something. And that's exactly what it is. It's all it is designed to do. It's designed to do two things. It's designed to reflect back your radiative heat to your body so that you don't lose that radiative heat. And then it just traps some of that convective heat inside that bag. It's super lightweight so that you can always have one with you. And it's, a great device. It doesn't do anything against conductive heat, but usually if you can find a nice soft spot somewhere to lay down, you don't have to worry about conductive heat anyway.
So that heat transfer, that heat loss, when you're not wearing your clothes, is that the reason that they say, like when somebody has hypothermia, to try to get as close to them as you can?
Yeah, so when somebody gets hypothermia, that means that their body temperature has gone down. They're losing heat much, much faster than their body can create heat internally. And that usually happens because they're wet or they're in contact with something very cold. But usually they've gotten their clothes wet and then their clothes have frozen and it's drawing heat away from their body very, very quickly. That's usually what happens. So there's two things that you do. First of all, you get in warm liquids into them because you need to warm up the core of their body so that their body can not work so hard to stay warm. So you get warm liquids into them, even lukewarm liquids or liquids that aren't necessarily warm but aren't cold. Anything kind of room temperature and above is good for that. And then the second thing is to get them out of those wet clothes so you can reduce that conduction. You don't want that conduction to heat away. Get them out of those hot clothes and get close to them. And it sounds a little bit kinky maybe or something, but usually you want skin-to-skin contact as much as possible because you want to be able to conduct your heat to them from the outside, get warm liquids in them from the inside, and heat them up. My older brother got hypothermia on a camp out once. He decided he was going to camp in his own tent by himself. Bad idea in the winter and snow because you want as many heat sources as possible in a tent and you don't want a lot of air around you to cause that convective heat loss. And so you want to have lots of people packed in your tent, lots of sleeping bags, dry clothes, and you want to have very little airflow, cut off all the airflow, and just get nice and cozy and warm. My brother didn't do that, and he ended up spending the entire next day, people forcing liquids down his throat and being cuddled up in a tent with my dad. My dad essentially spent the whole day in a tent just warming up my brother and getting him better. So I was grateful that my dad knew that because I learned that I was age 11, It was my first camp out as a Boy Scout, and I learned that at a very young age. So, very important thing to know if you live in a cold place, because you never really know when you might get stranded in the cold. It can happen in a heartbeat in Nebraska. You know, you can get caught in a blizzard without hardly any warning on I-80 and be stuck for hours or even a day or two. It could be really bad. And that doesn't usually happen, but it can happen.
Travel with at least half a tank of gas.
Yeah, you can travel with extra gas so you can keep your car and keep it warm, but also travel with blankets in your car and travel warmly clothed, even if you're in a heated car. I'm really bad at that because I hate traveling with lots of clothing on, but I try to stay smart. Okay, the last thing we're going to learn about is the greenhouse effect. And this is how it works. Light is coming from the sun. All kinds of light, visible light, infrared light, UV light, it's all coming down. And then it comes down and hits the earth, which has a high emissivity. So it mostly gets absorbed by the earth. Now, stuff that's coming down through the atmosphere from the outside, some of it gets bounced off into space, especially some of the ultraviolet, some of the blues, some of the purples get bounced off into space. And that's why the sky looks blue. It's because the blue light is getting bounced around up there and you see a lot of it. It's scattered a lot. However, longer infrared wavelengths cannot leave the atmosphere. They can't get in either. But once all these other lights get in and get absorbed by the Earth mostly starts to emit infrared light out, longer infrared wavelengths. And those ones can't escape the atmosphere.
At all?
Not very well. They're very inefficient at getting out. So they come out of the Earth, they get emitted by the Earth after it's absorbed all this other energy, and then they get blocked or reflected back, and they get stuck. And thank goodness they do, because without it, we would all be dead. Right? This is what keeps the Earth warm. This keeps the Earth habitable. We normally think greenhouse effect, terrible things, CO2 gases, the ice, the poles are melting or whatever. But really, this is actually what keeps us alive also. There's no doubt that if the Earth got too warm, it would be bad for the Earth. But there is a lot of debate on whether or not the Earth's present warming trend is natural or if it's man-made. I'm currently on the fence about it as a scientist. I've done a fair amount of studying of these things, and I think it is possible that we are causing some of the Earth's present warming, but I also think it's possible that we're not causing a lot of it. And I also think that we haven't taken the right kind of data. I think the data is very politically and economically driven. Right now, the people who study Earth warming, or whatever they call this science, climate change science, I have a hard time calling it climate change science because it's really just physics. But they've turned it into a science where you don't have to study very much physics to do it, which bothers me because a lot of the people doing it don't understand the physics behind it. That really bugs the crap out of me. They're mostly studying anthropology. They're kind of studying the history of the Earth and saying, well, the history of the Earth shows that it does this, and so obviously it should be doing this now. And that's kind of their whole science. It's more social science than anything else. But anyway, they don't understand the physics behind it necessarily, and that drives me crazy. But the point is that there is a fair amount of controversy because of the money driving it. The people who do all this climate change science have recently had their legs cut off from under them, because over 90% of the climate science money came from the U.S. government, and our present president has decided to cut that funding almost entirely. And I don't think that's a bad thing, personally. I think the science should be done, but I think it should be done by people driven by science and not by money. Because there have literally been trillions of dollars dumped into this over the years, since about the 70s. And they still haven't been able to prove anything. They've just got a lot of conjectures. And their models are really unconvincing to true scientists. And I'm not the only one. There are literally thousands of scientists who have signed petitions trying to get the federal government to stop dumping money into climate science, because we could use it in so many other ways, so much more effectively. And most of it is just going to companies that are buddies of some congressman, and then they go belly up and take the money and run. It's happened so many times. It's not just recently. It's been 40 years this has been happening. People apply for grants and take the money and just go. And a lot of the money doesn't even stay in the United States. It goes to Europe. We send probably half that money to Europe, which is ridiculous. Why are we sending research money to Europe from U.S. tax dollars? It makes no sense. But the point is, the politics have driven the science for a long time, and I really hate that. Not saying that I like what our current president is doing with science, not necessarily the truth, but he has certainly changed that particular aspect of political dealings in science.
Politics and science should be separated almost like church and state.
Yeah, and they are separated kind of like church and state, which is to mean that they're not. Right? Anybody who believes that the church and state in the United States is separated is not been educated on the political system in the United States. It's still very, very influenced both ways. And that's unfortunate but true. And then there are the people that think that religion and state should be included in that. That nobody in government should ever discuss religion. We should never have any religious anythings on a government property or anything else. You know, science and politics and government and socialism, social issues, none of them are separable. You cannot separate them. They are all part of the human experience. And I think that the founders of the United States understood this, but I think it was very difficult to perpetuate that idea through the ages. And I think it's been distorted many times, unfortunately. But it's part of our job as scientists to understand it as well as possible and to influence it the best we can as well. Here's a really cool device that a lot of people are using all over the world these days, solar cookers, which are essentially a greenhouse effect oven. They trap the sun's energy, and then it gets re-emitted and captured inside of this box and cooks things. And can cook things rather quickly, actually. While I was at college, one of the professors I had was building these things and sending them all over the world to third world countries, sending the plans and materials so that people could cook without firewood, particularly in like the highlands of South America where firewood is scarce, but sunlight is everywhere. So very good stuff there. Let's take a look at a problem here, maybe. I like well, right here they say the sun irradiates like a perfect black body. An emissivity of exactly 1. Not necessarily true, but it's pretty good. It's pretty close to 1.
Is it because it's radiating out so much that it's hard for it to absorb any?
No, that's not it. What it really is that it absorbs everything that comes at it and re-emits it. You know, it just doesn't have any reflectivity to it at all. It's anything you see coming from the sun was created by the sun. So let's do the car radiator problem here. Calculate the rate of heat transfer by radiation from a car radiator into a 50 degree Celsius environment. So we'll use that one. And I think we're done with this chapter at this point. Moving on to thermodynamics. And we still got time.
Are we starting that today?
Yeah, I think we might. Stretch load. All right. So tomorrow is when, Cassidy, did you by chance go by the Broken Bow extension today?
No, I was shadowing in Ord. I don't work in Broken Bow anymore, so.
Oh, you don't? Okay.
But I'm planning on having class at the college tomorrow because I have to take my car to the repair shop.
Okay, so you have some lab equipment that I sent you there today. It should be there, and a T-shirt.
Okay.
So you can pick that up there, and then when you're done with all that stuff, you can just leave it at the extension, and they'll send it down with somebody to me.
Okay.
So you should be good for this week and next week. So tomorrow, let's see. Tomorrow is the lab on. What were we going to do tomorrow?
CO2, CO2 stuff.
Oh no, that was a demonstration I was going to do today. I forgot. I got to write myself a note. I'll bring the dry ice tomorrow. Let me.
So tomorrow's lab is going to be The Martian.
The Martian. You want to watch the movie The Martian?
With a liter bottle.
That was the most.
Oh yeah, we were going to do Bernoulli's lab tomorrow.
I can
So if we do Bernoulli lab tomorrow, that means we're not going to end up doing a thermodynamics or a temperature lab, which means I'll do the triple point thing tomorrow too. So I'll do a demonstration of the triple point tomorrow, and then we'll also do the Bernoulli experiment tomorrow, which is a 2-liter bottle experiment thing. And let me make a note for myself to pick up some dry ice.
What's your email? 'Cause I've been sending you a couple emails. And I don't think you're getting through.
dailyj@mpcc.edu.
That's the email I've been sending.
I sent you. I got one from you today, and I answered it.
Oh, okay. Oh, okay,
So
cool.
subject, say tomorrow, dry ice. Dry ice. And then that means I have to get the dry ice in the morning. So I'm going to put it at time 7 a.m. And let's save that. Okay, so tomorrow I'll get some dry ice, and we will do some studying of the triple point experiment, and then next week on Wednesday we'll do our last lab, which will be we'll do a wave lab. We'll be doing some waves on strings. We'll try to finish up the thermodynamics chapter right now in the next hour or so, and then.
The whole thing?
Oh yeah, the whole thing, which we'll crank it out right now. Probably won't get through it all. But if we don't get through it all, we'll finish up next week and try to finish up the last 2 chapters next week as well. So we're going to be moving pretty quickly.
Are we trying to get number 16 or 17?
We're trying to get all the way through the hearing part, but the hearing one is not really all that scientific, really. It's just a lot of explanations, interesting things, cool stuff. But we'll definitely try to get through the waves one. Sound and hearing is a good one, but the waves one is definitely one we have to do. Yes?
So when it comes to the exam, like, will we not have questions on 12 since we didn't do homework?
Yeah, since we didn't do any homework in 12, we won't include any of those on the exam.
And with 13, you'll just take questions from the ones we were doing in the book.
That's correct.
Okay.
And I will try to program some of those into my open math if I can get the time to do it. I might be able to get that done by next week. And the final exam, while it's technically we're done on the 11th or whatever, if we need to do the final exam sometime at the beginning of the week after that, we can stretch it a little bit. Won't be the end of the world.
The last time we meet for class, so we'll be in the ninth.
Yes, 9th is the last time we meet. Any other questions really quick before we get back to it?
I
Well, let's get you in there and get it done tomorrow or the next day or something like that.
I'll put it over my roof for
So, okay. What time are you going to do it tomorrow? Before lab?
tomorrow. Yeah. For class.
Okay, good. Okay, so thermodynamics, heat, movement. That's literally what it means, right? Heat, movement. So how do we make heat cause things to move? Can you think of how it's done? Well, that's something that does it, but
Yeah.
how is it done? How can heat cause movement?
Well,
Combustion. Combustion.
But how? So you said turning a turbine, combustion, but what's actually happening at a very fundamental level? What does the heat do to make something move?
Faster.
Okay? It makes molecules move faster. What do the molecules do then if they're in a...
Push.
They can rise, they can push, they can expand. And if they're expanding, pushing, rising against something, then that something is going to move, right? That's really this whole chapter. We're done.
cool.
Just kidding.
See you tomorrow.
But that is this whole chapter in a nutshell. We need to talk about the details
The math.
and the math.
That is nice.
Come on, let's go. Okay, so first law of thermodynamics. Remember, we already talked about the 0th law of thermodynamics. Now we're going to talk about the first law of thermodynamics. And pretty much the first law of thermodynamics is one you've seen before, but we called it conservation of energy. So that's what this is. But it's just in a little different format, looks a little bit different. You have a delta U, which is the change in internal energy. So internal energy is the energy that is within the system that is causing the temperature to be what it is. That is the thermal energy that is creating the temperature, delta U, right? And that is going to be equal to the heat transfer, Q, and that's going to be the net heat transferred into the system. That could either be a positive or a negative number. If it's a positive number, the heat is coming into the system. If it's a negative number, the heat is leaving the system. And then you subtract off the amount of work done by the system. So if the work is being done by the system, then that work is a positive number and you're subtracting off a number. But if that work is being done on the system, then you're subtracting off a negative number, which means you're adding a number, right? So it gets a little confusing. These things all have signs that you have to keep track of and make sure you understand. But it's easiest for me to think of it in terms of the system losing or gaining energy. When the system is gaining energy, it is positive energy to that system. When the system is doing work on something else, that is positive energy that it does on something else. So these two things are positive when when the heat is being added to the system or the work is being done by the system on something else. But if the heat is being taken from the system, Q is negative. And if something else is doing work on the system, in other words, if the system is being worked on, being pushed, being squeezed, or whatever else, then this W becomes negative, and you get a double negative there, causing a positive. Now, if that doesn't confuse you, I don't know what will. So let's try to figure this out.
With the work part, like if I'm physically like squeezing a balloon or whatever, making like,
So the balloon is your system.
and I'm applying work to it.
You're doing work to it because you're squeezing it with a force and moving it.
That would
Right.
be increasing the internal energy.
That's right. So you're doing work on the system. That means that that W in the equation is a negative number because the system's not doing the work, you are. That changes that equation to a plus W because you end up with a double negative, which means you're adding energy to the system, which is true.
The energy is really specific.
So that's right. If you let go of the balloon after you've squeezed it, the gas inside the balloon will do work on its environment, pushing its environment outward. And then that work all of a sudden becomes a positive number and it loses energy to the environment. Does that make sense? Okay, that's good, because I don't know if I can explain it twice without screwing it up. But that is the first law of thermodynamics. And here is a representation of that. You're heating a system, energy is coming in. The system is doing work. Maybe it's a balloon and it's expanding because you're heating the balloon. So the balloon is pushing outward on a system, pushing the air around it away, right? But you can also have Q that is leaving your system, which would be represented by an arrow leaving the system out, and that would be a negative Q. And you can have work in, which is represented as a negative work. What happened to this thing? What did I just do? Okay, so anyway. So in the case, let's go back one actually. In the case of our steam engine, how is this working? What is this heat flow work thing like? Where is the heat going into? Where are you creating this thermal energy, first of all, in the steam engine? You're burning something in a furnace, right? Getting it hot, and that hot is being used to heat up water, turning it to steam. What does that steam do? As it goes from liquid to gas, what does it do?
Turning gears and
It expands. That's the first thing it does, isn't it? And it expands up against a what?
Turbine.
Usually in a steam engine, it's a piston, right? Not a turbine. In a modern locomotive, they use turbines. But in this one, they're using the steam up against a piston. The piston is connected to those drivers, those big old wheels on the locomotive. And those pistons push that wheel around and around. And if you're near it, you can hear it. You can hear it going choo, 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 right? And that's the piston pushing. You can even hear some of the steam escaping, right? And that is the work. It's expanding inside of that piston. It's inside of that cylinder, pushing on that piston. That's a force that is moving something a distance. Force times distance equals work. That is work that is positive to the steam engine because it's doing work on the environment around it. It's doing work on the wheels, which are not part of the system. Okay? That's what it's all about. Excuse me. So let's do an example. I'm going to transfer 40 joules to a system, and the system is going to do 10 joules of work. Later, there's going to be 25 joules out of the system, and 4 joules of work is going to be done on the system. We want to know what the net change in the internal energy of the system is. Well, our equation says that the net change in internal energy, delta U, is equal to Q minus W, but these Q's and W's are all net heats and net work. So you have to add all the works and add all the Q's together and then plug into this equation. So the 40 joules of heat into the system, is that positive or negative 40? Because it's going into the system, it is positive. That increases the energy of your system. That's positive. Well, not temperature, but heat going in, right? Heat going in is positive. Heat and temperature are not exactly the same thing, right? 10 joules of work being done by the system, positive or negative? If the work is being done by the system, it is positive, right? So energy that is put into the system is positive. Work that is done by the system is positive. But work that is energy that is taken out of the system or that leaves the system is negative, and work done on the system is negative, right? So we have a positive 40 joules for our Q and a positive 10 joules of work for our work. But then on the second part, we have 25 joules out of the system. That's negative. So we subtract 25 joules in our Q here, and then we have 40 joules of work done on the system. We subtract that off here. So our net Q is 15 joules, our net work is 6 joules. They both end up positive, just because of the circumstances. And then we plug them into our equation for delta U. The change in internal energy is going to be 9 joules of energy. Okay? If you do it for each step, you'll find the first step, there's a net gain of 30, and the second step, there's a net loss of negative 21, and you add those together to get a total of 9 joules, just like we did before. Then they want to know if, what is the change in internal energy of a system when a total of 150 joules of heat transfer occurs out of the system, so that's going to be negative, and 159 joules of work is done on the system, so that's also going to be negative. Well, in this case, you're going to have Q is going to be negative 150, you're going to have W equals negative 159, and then you have negative 150 minus a minus 159, which is also 9 joules. It has the same overall change in internal energy, but it's a very different thing that happened, right? In this one, a ton of heat left the system while something came in and squeezed the system, right? Very different than before. Before, we had, first we had 2 steps, right? We had 2 steps, we had 40 joules of energy entered the system, while the system expanded, and then we had 25 joules of energy leave the system while the system was compressed. So that's very different. But it ended up in the same amount of internal energy. So you can reach same amounts of internal energy by doing different things to systems. And this is extremely important in thermodynamics. Because in thermodynamics, you don't want to just heat up your gas, expand the piston, and turn the wheel a quarter of a turn on your locomotive. What do you really want to do? You want it to keep turning. You want to get back to the point that you started and do the process again, and again, and again. That means you always have to return back to where you started, which means you need a process that will get you from where you started to a different point, then from that different point to back to where you started, but those 2 paths can't be the same. Because if those 2 paths are the same, what's going to happen to your locomotive? You're going to go forward
And then back.
and then backwards. You want a different process to take you back to your original internal energy so you can start the process over again. And that's the whole idea behind thermodynamics. Take one process that'll do one thing, a different process that'll do something entirely different, maybe even unrelated to what you did before, and then go back and do the same thing again so that you can keep doing that same thing over and over again. Not very efficient necessarily. Because every time you do that other process that just gets you back to where you started without taking you forward or moving you up or whatever you're trying to do, it's doing something that's maybe not necessary for the movement you're trying to accomplish or the thermodynamics you're trying to accomplish. However, what it does do for you is it allows you to create a cycle that is repetitive and you can do over and over and over again. This is what we call, can you guess what it's called? An engine. This cycle of thermodynamic processes that takes us from one type of internal energy back around to another one, then back around to the same one, and then back around to another one, and back around to the same one. It's called an engine cycle. And the devices that do this are called heat engines. So, here they show the 2 different processes we were just talking about. Heat in, work out, heat out, work in, and so on and so forth. Ends up with the same amount. It turns out that our body is actually a heat engine. Although not in the same way that a locomotive is, it still follows the same laws and has similar processes going on. In our case, in humans, we have food that goes in, right? So we have an extra thing on our equation here. We do some work, we move things around, we lift things, we walk, we talk, our hearts beat. All these things are considered work. But we also have some heat leaving our system. And thank goodness, because if it didn't, we would all be fat. Really, really fat, right? So that heat leaving is actually a huge amount of the energy that we take in food every day. The amount of food that we take in every day, about half of it is just to keep our body warm. Okay, so that half of the food we eat every day is burned off just by us sitting around being warm. All right, let's take a look at some of these questions here really quick.
Are we gonna, is this for homework as well?
Yep.
So do you want us to just read these problems and like hand them to you?
Yeah, just work these out and turn them in just like a traditional homework assignment.
Did we get questions for 14?
Are we in 15?
Here's the
Yeah. Yes, we did.
3 questions, I think.
We did 3 questions for the last 3 sections, but did we do any last time?
Nope.
Did we want to? I don't even know.
Did you want to or did you want
Temperature change. So we didn't do any for 1, 2, 3, and 4.
No, we didn't.
We definitely should do some for 2 and 3. So let's go back and do some questions for sections 14.2 and 14.3 really quick. So let's do the one that says a 0.250 kilogram block of pure material is heated from 20 to 65 degrees by the addition of energy. Calculate the specific heat and identify the substance that it's made of. That's a good one. Let's do the number of kilocalories in food determined by burning the food and measuring the amount of heat transfer. It's a good one. Hey, here's a spent fuel pool at a nuclear reactor. I've stood on top of one of those. All right, let's do 14.3 really quick. Oh, I'm tired. Let's do this one right here. On a certain dry, sunny day, a swimming pool temperature would rise by 1.5 degrees Celsius if not for evaporation. What fraction of the water must evaporate to carry away precisely enough energy to keep the temperature constant? That's a good challenging one right there. And how about this one right here? In 1986, a gargantuan iceberg broke away from the Ross Ice Shelf in Antarctica. You want to know what's the mass, how much heat transfer needed to melt it, how many years would it take to do it? So that's actually one of the classic arguments for global warming right now, is that this ice shelf on one corner of Iceland, of Antarctica, has been receding and chunks have been breaking off of it and melting. But it's always just this one little corner of Iceland that's near South America. They never talk about the rest of Iceland, of Antarctica. They never talk about the rest of Antarctica. They also talk about Greenland a lot, the ice shelf on Greenland, and how much it has receded. Well, Greenland is such a tiny percentage of the freshwater ice in the world that it's not even worth talking about in most cases. It's just a tiny piece. The big piece is Antarctica. So if you're going to talk about global warming and ice melting, you have to talk about Antarctica, and not just a piece of it. You have to talk about all of it. And what they never tell anybody, which is well known to all of them, is that the rest of the Antarctica ice shelf, which is the biggest freshwater ice sheet on the planet by far, it's like 90-something% of the freshwater ice is on that ice shelf that's like 2 miles thick. The rest of it, besides that one little peninsula by South America, is actually growing, and is growing faster than the part that is shrinking. So like 75% of the ice shelf is growing while 25% of it is receding. And the part that's growing is growing faster. And it makes Greenland totally mean nothing. But they keep using this melting ice shelf as evidence for global warming because that is what makes people angry. That's what makes people think something bad is going to happen. The funny thing is that an increase in ice is just as much a factor, just as much a telltale sign of global warming. It is inevitable that parts of the Earth that are not covered in ice will be covered in ice when other parts get warmer. It is inevitable. It will happen. It always has. It always will. So they could just as easily say, look, the ice shelf on Antarctica is getting bigger. We're experiencing global warming, but they don't want to look stupid because they know that most people will think, what are you talking about? That doesn't make any sense. But it is true. So it's kind of funny. Again, that's just another example of how these people are manipulating people to make them believe their science and to get money for their research labs, which really is not for their research labs, it's for their own personal lifestyle. Yes, yes, sir.
It was this is a question of whether a movie got science right. The Day After Tomorrow.
I have seen it. I own it.
Is that one like accurate as far as the science, the fact that global warming would disrupt the
It's a possibility for sure, but not like.
It's kind of carried to an extreme for theatrical benefit, but
Yeah, I mean, there is actually evidence of extreme cooling on the planet in many cases, and very quick ice ages. There is evidence of that. So that is not that far off the mark. The cause for it, we don't know anything about, and that's the thing. That's the thing about that movie that is bad. They show here having these computer models that predict all these things. There is no such computer model. Nobody has one, and nobody will. The math is too hard to do, and they make it look like it's something that we already know how to do. It just isn't. If we knew how to do that, we'd be able to predict the weather for 8 weeks ahead of time. We can barely do 8 hours this past couple weeks.
especially in Nebraska.
Did you see how often the rain prediction changed over the past 3 days? It was on a half-hour basis. It's going to rain every day. Oh, it's not going to rain for another 2 weeks. Oh, it's going to rain every day. So we're going to get this huge thunderstorm. Oh, we're not going to get a drop. And it was just crazy until like the moment it rained, we had no idea what was going to happen. If we could predict what was going to happen with a computer model, we would be able to do it. Okay?
Like in Back to the Future, too.
Yeah. Weather is just impossibly difficult because it has so many things that affect it. The sun affects it, the oceans affect it, the land affects it, everything affects it. Yeah, I mean, there's some butterfly flapping its wings in Tokyo affects it. Whatever. This crazy stuff affects it. It is definitely chaos theory. So you cannot really base a science on it very easily. It's kind of goofy. Okay, let's.
It's a work of fiction where people start going back in time and everything. You say all this one about see what they accidentally steps off and crushes the butterfly and that creates everything up.
Where were we? Were we in chapter 15 just now?
Yeah, is that all the homework for chapter 14?
Yeah, let's do that'll be all the homework for chapter 14.
7 problems total.
Yep.
Can you tell me what did they just write down the first words of those other problems? Because I must have missed that.
So we're talking about chapter 14 still?
Yeah, those other questions, like the 3 that you got earlier. That
So Andrew has them. Can he just email them to you? Would that be easiest?
Yeah.
Okay, you want to just
You want me to just tell her? Or
it'd probably be easier to email so she's not flipping through the book on her computer.
Okay, I just wrote down what section
Okay. Yeah. You can either do you have her email by chance?
No, I don't.
Okay, send it. Just email me that, just a picture of your homework page or something. Email that to me and I'll email it to her.
Hey, sorry about that.
No worries. It's understandable. We're kind of flying by the seat of our pants at this point. Okay, so thermodynamics, first law of thermodynamics. First law on simple processes is where we're at. So let's do some simple processes. So here is the basic idea of a heat engine. You have this system of some kind that you put heat into, and it does some work, and then some heat leaves it. Believe it or not, the heat leaving is absolutely essential. It has to go in from one side and leave from another side, or go in from one source and leave to another source. There has to be a hot side and a cold side for a heat engine to work. So let's talk about a couple of engines that we're familiar with. Car engines. A car engine is a type of heat engine. Where is the hot side of a car engine?
Inside the, like, where the piston is,
There's an ignition that lights a bit of gas and air and creates an explosion. That's your hot, right? And where's the cold side?
Back into this. Well, that's the work out this
Yeah, the back end of the piston is where the work is done.
way. The coolant side.
Yeah. So everywhere there's coolant on the engine, and everywhere the engine is touching the air, and everywhere you're trying to cool off your engine, everywhere you touch that engine and it's hot, but the air around it is not, right? That's where the heat is leaving the engine. That's the cold side of your engine. Okay? You have to have a hot side and you have to have a cold side. And look at this. The Q in is the amount of heat going in. The Q out is the amount of heat going out. And if you take the difference between those two, according to the first law of thermodynamics, that will equal the work done. Right? That will equal the work done as long as your delta U is 0. As long as the temperature inside your engine stays the same, which it usually does. It's usually pretty hot. But as long as that temperature stays the same and you solve this equation, the work done by the engine is equal to the difference between the heat coming in and the heat going out. So how much work can you do if your engine is in a really hot place?
Not a lot.
Not very much. Why?
Because not enough heat.
Because the difference between your Q in and your Q out is going to be not very much. So you won't be able to do much work. Is that true of car engines? When it's hot outside, does your engine work harder? It does. It has to act. It doesn't work. It doesn't. Work harder is a bad thing to say in a physics class. On a hot day, your car is not very efficient. It cannot put out as much torque. It cannot put out much energy because the difference between the engine heat and the outside heat is smaller. They work much better in cold. Much better in cold. Right? Much more efficiently. So that is very important for efficiency. Here is the model of your standard piston type engine, and there are many kinds of piston engines. Some of the more famous ones are the diesel engine, the combustion engine like we use in our automobiles, the Stirling engine, which I will show you in just a minute here, the Carnot engine, which is the ideal engine, which nobody's ever been able to replicate.
so there's only one?
What?
Carnot engine or whatever, there's only one of them?
Well, no, it's theoretical.
Okay.
The Stirling engine is as close as you can get to it, practically speaking. Yes.
Could you make an engine where you put like this gas in a tube and you superheat it and supercool it?
Well, good question. Let's do it. Don't even have to super it. You can just heat it and cool it. This right here, let me bring it up to the front of the classroom. Actually, I have two of these. Which one should I use? Can't find my rug, so I guess I'll use this one. Let's try this. I'm going to try this one as well. So both of these are Stirling engines that are just a piston that is sealed up with some air in it. So this one right here, this is the piston, and it's got a little copper thing on the end with a little alcohol lamp so you can heat up the copper, and that will heat up the piston, which will expand the gas inside, or heat up the cylinder, which will expand the gas inside the piston, and then inside the cylinder, pushing the piston and turning this wheel. And all it needs is to be heated on one end, and it's got these vanes on it that cool it on the other end. And as the piston goes back and forth from the hot part that's being heated to the cool part on the other end, it gets hot and then it cools, and then it gets hot and then it cools.
I think I've heard of this. It doesn't, it's only one, it's one of the only engines that works in reverse. So you heat it and you
That's
get
right.
work, you put work in and it comes out cold.
So let's demonstrate it here. Let's see if we can make it work. I need some alcohol and a match.
Are you allowed to have alcohol in this building?
Oh, well, plenty of
We'll use green alcohol.
depends on what kind of bottle it's in.
Next to the nursing home is probably a
There was this old movie from it was right after they started having movies in color. And it's like this guy who sees the ghost of the pirate.
On
The ghost can like interact with things. And he,
Blackbeard's Ghost.
I think so. And the ghost drinks anything and everything with alcohol. They're in a nurse's station, everything. And he like pops open a bottle of alcohol.
Okay, so this is my green alcohol. It's a mixture of ethyl alcohol and wood alcohol, I think, like rubbing alcohol. But what I'm going to do is I'm going to just take this little oil lantern cover off here, if I can. There we go. I'm going to fill up this little thing here with some alcohol. Very simple. So it'll burn a little bit. Spill it all over my fingers so that when I light this up, my fingers light on fire. Okay, now I've got my wick in there and it's going to start drawing up alcohol a little bit. Try to do this without lighting my computer on fire. No promises.
The stream suddenly ends, you know why.
See if I can put this high enough so that you can see it there.
Sort of like the chemical watch.
Not quite. I'll have to lift it up after I light it. Let's see. Where's my lighter? You guys should be able to see it up on this screen if I.
Or like a lighter.
No, that didn't work. Where's my. I'll bring it up on my photo booth camera. Can't see it. But anyway, I have a lighter here somewhere. Where's my
Can
lighter?
Cassidy still see it?
I'll lift it up once I do it so that
No, I
she
mean,
can see it.
It looks like the screen is gone.
Can you see my screen, Cassidy?
Yeah.
Okay. Okay, I've lit it up so you can see that it's on fire there, and it's slowly heating up this side of the cylinder. So the gas inside the cylinder will start expanding. Usually this needs a little kickstart once it starts getting heated up. And this actually has two cylinders. It has one on this side and one on the other side. And then it has a little thing that passes in between that transfers the heat. It's like a little slider, a tube. So as this one heats up, it heats up the gas, and it pushes the slider over here, it heats this one. So as this one's getting pushed by the heat, this one gets pushed a little bit later so that it keeps it going. Let's see if we can get it started here. You can see that it's kind of trying to start. I've always had trouble with this one for some reason. Come on now. Go, go, go. It's trying to go.
Do you need something that will burn hotter?
No. You can see it's like, I want to go.
I think it's starting to move just a little bit.
I don't know which way it wants to go either, so.
If you just give it a minute, I think I see it moving a little bit.
Yeah, it is trying for sure. You can see it start to. Come on, baby. It's trying. Okay, I'm going to let it go there for a little bit, and then I'm going to go get some hot water to do my next one.
Mr. Baylor's going to come to run use the restroom.
Good. We'll let that heat up while I'm getting my water hot.
Just left over from the Senate, but you know, we get all the vegetable and sausage. Also, mushrooms and onions. 2 to 5.
Any luck?
Not that I can tell from here.
Let's try again. Man, I can feel it trying to move, but it's just... just won't go. Okay, I'm going to try the Bunsen burner. We'll really heat it up.
Are you looking for your spark plug?
Turn the camera this way, just in case it works.
Don't try this at home.
No, definitely go to a neighbor's. Oh man, I'm leaking alcohol all over the place. That's going to be bad.
On top of the Bunsen.
Oh God. Let's hope it don't tip over. Hey, you lit the wick.
Come on. Come on, baby, let my fire.
Watch Andrew walk in as the page catches on fire.
Or just blame him.
Man, it wants to go so bad. It's so close. Come on, come on, come on. Come on. It's not quite. Come on. It's trying.
We gave up on straight alcohol. We just stuck it in the Bunsen burner.
I think the lamp area is on fire because
It was looking like a really good idea when the alcohol spilled out of the machine all over the paper.
Yeah. So now I got fire all over my table, right? So. Woo! Yeah, okay.
Oh wait, Cassidy, you missed that.
No, she can see it on the screen.
I couldn't see the flaming table.
Okay, we're going to try the other engine. There's another type of stirring engine.
I was waiting for you to walk in just as the page caught fire. Just see you standing on the table with burning pieces of paper.
engineer work, I set fire.
You walk into the room 3 minutes later and burn it.
Okay, so with this one is really cool if you have some dry ice. I don't happen to have any dry ice right now, but I might be able to do it with some alcohol and regular ice. We'll try that in a minute. But this one, I'm literally just using some boiling water. So I'm going to pour some boiling water in this beaker here. And it's going to be steaming like crazy. And I'm going to put this engine. So this engine's essentially the same kind of engine, but it looks very different. It's got 2 pistons on it. And one of the pistons is connected to a little membrane on the top of our cylinder here. Here's our cylinder. It's just this flat pancake cylinder on the bottom. And it's got this little yellow piece of foam in it. And that yellow piece of foam will get hot. And as the air inside this cylinder heats up, that foam will actually rise to the top and carry some of the heat to the top and allow the heat to escape. And as it escapes, it'll fall back down to the bottom. And then it will make this thing turn just by having some steam under it. So we'll heat it up a little bit here and we'll get her started. Don't tell me this one's not going to work. Come on.
kind of kept going for a while.
I need some more water. It's very
It's turning
close.
very slowly.
Yeah,
I
it'll
think
go.
it's going clockwise right
Let's see here. That's the direction right there. It wants to go that direction. You can kind of see it going. I'm not sure if I quite got the water hot enough, but you can see that it's trying to
there
go.
it
There we go.
Cool.
So it's just, and if you look down at the bottom of it, you can see that hot. So if you look down at the bottom of it, you can see the, maybe, there we go. You can see that yellow thing moving up and down, carrying the heat from one side to the other, so that it goes in on the bottom and it goes out on the top.
Can't take off.
And that is a Stirling engine. All it requires
can-
is a hot end. Now let's try it with a cold end. I'll be right back. See if I can get some notes.
So,
Definitely going on Snapchat.
what this is telling me is that I'm going to be building a plane that has a propeller made with a Stirling engine, specifically for takeoffs. And then I'll just have, you know, whatever else on it for the rest of the time. But
That actually sounds pretty cool.
I want a plane that can take off purely by, or even better, you put it on a spacecraft, and then when you just get, when you're ready to move, you just flip your side facing to face something
So my
like the
ice
sun.
is stuck in the freezer. I won't be able to get it out. But tomorrow when we have dry ice, we'll do it with dry ice. Because you can't, all you need is a temperature difference between the top and the bottom. In this case, we have a hot bottom and a cool top. But if we put this on a block of dry ice, it will create a warm top and a very cold bottom. And this thing will also turn. But guess what's going to happen to it?
You're going to turn reverse.
It's going to turn in the opposite direction. Instead of the heat transferring from the bottom to the top, it's going to have to transfer from the top to the bottom. The pistons will be going in the opposite direction, and so will the propeller.
So I'm going to go
So if
really
we
fast.
put a piece of dry ice here and the boiling water underneath,
If you put dry ice there and just warm air underneath, it'll work. It'll
Right.
work the same direction
go
as it is now.
faster if you put the dry ice on top?
Oh yeah, if you do hot on the bottom and dry ice, it will definitely go faster,
Okay.
for sure.
There's
So, in fact, you can slow it down just by putting your fingers on
by
top.
boiling water.
If you warm up the top for long enough, you can actually slow it down. I'm not doing a great job of it. But
You can hear the difference.
yeah,
Mm-hmm.
it definitely changes it. So anyway, that is a Stirling engine, one type of heat engine.
if you had enough, would you ever be able to make like something fly based off of that?
It'd be difficult because while this is a very efficient engine, it doesn't have a lot of power. It's an extremely efficient engine, which is why you can do it with such a little amount of heat. But the power involved is not that great. Now they have made Stirling engines that are used to turn turbines for making electricity, used to turn generators for electricity. And they just put them on these, you know, they put them on one of these big dishes that they used to use for TV. And they put the Stirling engine on the end of it, and they reflect all the sunlight to the Stirling engine on the backside of the Stirling engine, and then turn a little generator at that. That's about as much as you can do with a Stirling engine. They just don't have a lot of torque.
So if you could theoretically, like, if you had somebody like Micah, for instance, who's pretty small, and you put him in like basically just like you know, like the planes that don't have like an engine, they're
No,
just kind of gliders.
You'd never be able to,
Take it off.
yeah, because you'd have to pull along your heat source. You have to have something that's hot, right? So it's never going to. This is the reason we don't use Stirling engines. We use combustion engines. Because combustion engines are not nearly so efficient, but they are much more powerful. They have much more torque involved. All right, so let's get back to it here. Where were we? What is this thing? This? Yeah, go right ahead. So that is the idea of the engine and the piston moving, one of the types of engines that we can use here. So how are we going to make this go around in this cycle? Like I said, we have to end up at the same point every time so we can go back around and do the same thing again and again and again. But what's going to happen? Here is our piston, which is our basic engine. You put in the heat somewhere. It expands the gas inside the piston, which pushes the piston upward. That piston can do some work, but it's all about a volume that is changing because of the pressure that's changing inside of it. It's a pressure change. It's a pressure times a change in volume, is what it is. And then it can be a change. It could actually be a change in. Well, a pressure times a change in volume is what we call an isobaric process, which means the pressure doesn't change, but the volume does. So as you heat up this thing, if you held the piston down, the pressure would build up. But if you allow the pressure to just push on that piston, the pressure doesn't change, it just opens up the volume more. So the heat essentially changes the volume. When the heat changes the volume but not the pressure, we call that an isobaric process. And if we put it into a PV diagram, remember the PV diagram is pressure times volume, an isobaric process looks like a straight horizontal line going from one volume to another volume staying at the same pressure. So in this case, it's going from volume A to volume B, that's our change in volume, and then the pressure is constant, so it is a flat line there. Isobaric. Now there are other kinds of processes as well. This one here, the pressure changes at the same time as the volume. It starts up here at this high pressure and this low volume, and then as energy, actually it starts here, the arrow here tells us which way it's going, so it's actually starting at point B. So starting at a big volume, low pressure, and then the pressure increases, it goes up as the volume decreases. And this is the case when you squeeze something. When you press the piston in and it compresses that gas in there, it increases the pressure of the gas while the volume goes down. That's what that that is that process right there.
So pressure and volume are kind of inversely proportional
Well, they can be. They don't necessarily have to be.
in that instance.
In that
Like
instance.
piston.
Yeah. They can, and they may or may not be directly or inversely proportionate, but they also may be a variation in that. But anyway, there's another one also where the volume stays constant. If the volume stays constant, then you're going on a vertical line path. You could be going from A to D or D to A or B to C, where your volume stays the same and the pressure changes. In other words, you're adding energy and you're not allowing it to expand, not allowing that piston to move, so the gas tries to expand and just increases the pressure in the volume inside the cylinder. That's called an isochoric process. Now, if you combine isobaric processes and isochoric process, you can make a loop. Let's say that we start at point A and we go to D. Actually, let's start at point A and go to B. So we're at a pressure of 1.5 times 10⁶ Pascal, and we're at a volume of whatever this volume is here. Then, keeping the pressure the same, we allow the volume to expand as we put energy in, as we put heat in. So we're allowing it to expand without changing the pressure. Then we stop it from expanding. We stop the piston and hang on to it. We don't let it do anything while we go from a high pressure to a low pressure. Okay? And then, how do you go from a high pressure to a low pressure without allowing the volume to expand? No, not necessarily. You can also cool it down. So this is the part where the engine cools right here. You allow it to cool, the pressure goes down, but the volume, and you hold the volume the same. Then all of a sudden you have a low pressure and a big volume. So then what can you do? You can allow the volume to drop without losing pressure, right? And then you want to go from a low pressure back to a high pressure without changing your volume. What do? You add heat. And then all of a sudden you're back to where you started. So you've gone through these four processes, each one of them different, and you've got back to the place where you started, so you can start again and go around and around and around. This is how an engine works. None of them are like this. It's very difficult to have isochoric, isobaric, isochoric, isobaric all the time. It doesn't work out so well. It can be a very choppy kind of an engine. But any kind of loop will work. Any loop that ends where it started and can go back around through the loop just by adding some energy in some way, is a great type of engine. You can keep it going just by adding some energy at a certain point in time in the process. But one of the interesting things about these PV diagrams is like we said before, which is the work is equal to the area under the curve, or in this case, the net work is equal to the area enclosed by the loop. So if you can calculate the area that's enclosed by this loop, you can calculate how much work was done total by this process. So that's why we like PV diagrams. So let's look at, we're gonna use this diagram actually here in figure B, which is this one here, and we're gonna calculate the work done in that process. It's gonna go from A to B to C to D to A, and we're gonna use the following methods. We're gonna use calculating the work first, and then calculating the area to calculate the work. So if we calculate the actual work done from A to B using pressure times change in volume, we get 750 joules. Then from C to D, pressure times change in volume, you get negative 100 joules. And then you add it, you add those together, and you get 650 joules total of energy done. Now, why would we only do A to B and then C to D and take the difference, or add them together? Because the area here is the area under this curve and the area under this curve subtract, right? That's what they did. They essentially calculated the area of this big rectangle and then the area of this little rectangle, and then they took the difference, and that got the area of the rectangle in the middle. So that's what they did right here, calculating those works. Well, if you're just going to calculate the area of that rectangle, it's the difference in the pressures times the change in the volume, and you get the same number, 650 joules. So it works either way. It's the same calculation. Now, here's some other processes. Two processes, one called isothermal and one called adiabatic. Isothermal means the temperature doesn't change. Heat is not allowed to isothermal means the temperature is not going to change. The change in temperature is going to be 0. And that can be done one of two ways. Either you can isolate the engine completely from its environment by surrounding it by like 10 feet of foam, or you can do the process so quickly that the temperature can't change because heat doesn't have time to escape.
Which is what our engines do, right?
Which is what our engines usually do, right? Then there's the adiabatic curve. Notice that the isothermal curve has a slightly less change than the adiabatic curve. In other words, it goes down less as you go off to the right, whereas the adiabatic drops down more. So they're not exactly the same kind of curve. They are slightly different. But the adiabatic curve is the curve where Q equals 0. So the heat transfer is equal to 0. So one of them, the temperature change is equal to 0. In other words, the internal energy change is equal to 0. The other one is where the heat exchange is equal to 0. Well, actually, the heat change is the one where we do very quickly. Anyway, I think both of them work out this way. But these ones are interesting because they actually allow us to create the ideal engine. So here are the different processes that you can have ideally, but in real life you never really can do any of these ideally. And the ideal engine, however, is going to use them. So let's see, what time is this class over? 6 o'clock? Yeah. So let's take a look at the homework here really quick. Let's look at, let's do this one with the hand-driven pump really quick. No, let's not do that one. Yeah, let's do that one. So the hand-driven pump, hand-driven tire pump is going to be the problem that you're going to do from this section, the only problem. Hand-driven tire pump has a piston. That's the one you're going to do. Next section is second law of thermodynamics, the efficiency of heat engines. So we already talked about the fact that you have to have a hot side and a cold side, and the bigger the difference between the hot and cold side, the more work you can do, which really means you're more efficient. So we've already kind of learned this, but what is the math behind this?
So, real quick, sorry, I'm having pencil trouble. Which question are we doing from?
We're doing the one that involves the tire pump.
The tire what?
The tire pump. The tire pump is,
That's from 15.2.
yep,
Do we have any from 15.1?
nope. So, now we're into the second law of thermodynamics. And it says here, the second law of dynamics says it is impossible in any system for heat transfer from a reservoir to completely convert work into a cyclical process in which the system returns to its initial state. In other words, if you have one of these loops in a PV diagram that constitutes an engine, you're always going to lose some energy. Okay? You're always going to lose some energy. So, in order to calculate the efficiency, here is the equation. Can you determine anything from looking at this equation?
What's the QH and QC? Oh.
That's the heat. The heat coming from the hot side, going into the hot side of the engine. QC is the heat going out of the cold side of the engine.
It can never be greater than 1.
Okay, so your efficiency can never be greater than 1 because QC over QC is always going to be less than QH. So that number QC over QH is always going to be a number that is less than 1. And 1 minus a number less than 1 is always going to give you a number between 0 and 1, right? Have we ever can we ever have an engine that is 1, the perfect efficiency?
No.
No. Can you make an engine that has the cold side and the hot side equal to a 0? Can you have a 0 for your cold side, for example?
Well, not really.
No, you can't. You cannot achieve absolute 0. It can't be done. Right? Well, and we're not even talking about temperature here, we're talking about heat transfer. But we already decided that for an engine to work, heat has to go in and heat has to go out. So there's always going to be a number in both of those spots. And the bottom one is always going to be bigger than the top one. So we're always going to have an engine that is imperfect. Okay? And that's exactly what we need to understand. Then the next thing we need to understand is what is the best engine you could possibly theoretically make? Let's first do an example here before we answer that question. We have a coal-fired power station. It's just a huge heat engine. Okay? You're putting heat in, burning coal. You're getting some work out, turning turbines. You're getting some heat out in the smokestacks and in other places, all kinds of places really. We want to know what is the work done by the power station if we have heat transfer from the coal of 2.5 times 10 to the 14, heat transfer into the environment of 1.48 times 10 to the 14 joules. And we want to know the efficiency, the combustion process, the following chemical reaction. So we're talking about kilograms of coal that are being used to do this, and so on and so forth. But first, let's talk about this one. What is the work being done? QH QH minus QC. You get 2.5 minus 1.4 times 10 to the 14, 1.02 times 10 to the 14 joules of work done. That's a fair amount of work, right? If the efficiency is the work divided by the QH. So work divided by QH is 0.408. Believe it or not, that is dang good. That's a pretty good efficiency for a coal-fired power station. Okay, this must be a pretty modern one because most of them are down in the 30s. Not too efficient, but it's economically efficient because coal is so cheap, right? You can burn a lot of coal without spending a lot of money. How about the daily consumption of coal from this amount of energy, right? So the daily consumption of coal is going to equal the heat from the coal that is consumed every day is the heat that's going in, right? So that's the 2.5 times 10 to the 14 joules. And then in the process, it's coal, the carbon plus the oxygen creates CO2, and it's, let's see, every 12 kilograms of coal, you're going to have 16 kilograms of oxygen. times 2 because there's 2 in every oxygen molecule. And you get 44 kilograms of CO2 for every 12 kilograms of coal. But they're putting in 1 times 10 to the 8 kilograms of coal. So you get out 3.7 times 10 to the 8 kilograms of CO2, which is an important number if you're trying to figure out how much CO2 is in the atmosphere. Why do you care how much CO2 is in the atmosphere? Because that's the gas that actually traps that infrared light that causes the global warming. Now, does anybody know how much CO2 is in the atmosphere as a percentage?
Less than 1%.
Less than 1%, quite a bit less than 1% actually. It's a very, very, very tiny amount. Another thing that has caused a lot of controversy as to how much we're putting in compared to how much there is in, if it's actually a significant amount. Some people think it is, some people think it isn't. There is no definitive answer. We just don't have enough information.
It's at the global average concentration of CO2 in Earth's atmosphere is currently around 0.04%,
Yep.
400 parts per million by volume. There's an annual fluctuation of about 3 to 9 parts per million, which is negatively correlated with the northern hemisphere's growth.
Yep. So it's kind of interesting, right? Another interesting thing about this whole thing with global warming is what breathes carbon dioxide? Plants. Trees in particular. Trees breathe it like crazy. Are you aware that the number of trees growing in the United States has nearly tripled since 1950, 1940?
I do that
Why?
because you gave it a lot. No, I mean,
Because I've told you this many times. Because of paper. It really comes down to paper. We use triple the paper that we used to use. We use so much more paper and so many more things. And paper is grown on trees that are planted by people. They cut down a tree and then they grow 2 in its place every time because they're planning their economic future. So the paper industry, which ironically is also one of the enemies of the environment, we're cutting down trees, has actually contributed more trees to the environment than any Greenpeace activist has ever dreamed of.
because they're influenced by green.
Because they're influenced by green and not the tree green, right? by the green made by linen instead of trees. So it's really kind of interesting. Nobody addresses that in the issues, though. Nobody talks about that. And so this is one of the reasons there is that great controversy out there about global warming. It's not just political, it is also scientific. There is a scientific controversy which drives it in the end.
And it doesn't come down to just the number of, this is how much CO2 we're producing, this is how much
Well,
in the atmosphere. It's a lot more complicated.
It is, not only because it's not just about one thing, but also the measurements that they're making are pretty minuscule compared to the size of our atmosphere. They're measuring these things in a few places when the atmosphere is incredibly huge. The Earth is incredibly huge. We have no idea what's happening to the CO2 concentrations in most of the atmosphere, just in some few spots. And you saw the variation. It's pretty dramatic. It changes a lot. And so their error bars are bigger than their data points, which in most science means your science is crap. But in theirs, they figure that's just the way we do it, so we're good. And it's aggravating. It's aggravating to scientists that most of the money in science in the past few years has gone to this kind of research. They can't even demonstrate what they're doing is viable. They just figure since they have the money and the backing of important people that it is of course viable, which of course works for most of the world. And it's not the first time. This has happened in many issues over the years. Many issues that I agreed with, many issues I didn't agree with, many issues that I don't even know about. Science is extremely driven by politics, and it's rather unfortunate. So, anyway,
Mystery.
yes.
There's an article I found, I was just searching around, it said that the EPA says that around 3% of atmospheric carbon dioxide is caused by humans.
Yeah, about 3%. About right. So here we go. Different types of engine processes now have been named for people who figured out that they were good processes or whatever. the Otto cycle, which is essentially the diesel engine cycle. It has two adiabatic curves where the heat exchange is 0, and then two where the heat comes in and go out that are isochoric, change in volume, or change in pressure, but no change in volume. That's essentially the diesel cycle, the Otto cycle, and it's pretty efficient. And then, oh, they don't show the Stirling cycle here. Do they show it later? Nope. Yes, they do. Okay. So that's the Otto cycle. Then the next one, let's actually do let's do a problem here really quick. Let's do this one here where it says how much heat transfer occurs to the environment by an electrical power plant station. Uses 1.25 times 10 to the 14 joules of heat transfer. So, the electrical power station problem right there. Okay, next. Now the perfect heat engine cycle. Carnot. As Carnot just started studying this stuff, he was able to theoretically devise the perfect heat engine. And here it is. Have you guys ever seen this toy?
Yes.
The drinking bird. That is the perfect heat engine. Unfortunately, it only is perfect if it works perfectly, which it never does. But if you can get one of these things going, and you have an endless supply of water that it can dip its beak into, and you can keep the temperature in the rest of the room at this right temperature all the time, which requires all kinds of work to get it done, then this engine will keep going forever. It's extremely efficient, and it's very nice. But it, again, doesn't... It is extremely theoretical, and it doesn't have a lot of torque involved either, just like the Stirling engine. But anyway, the Carnot engine consists of two adiabatic expansions here and here. Well, one adiabatic expansion here, one adiabatic compression here, an isotherm here, and an isotherm here. Now, what's an isotherm? The isotherm is the one where you do not change the temperature, right? Adiabatic is the one where you don't exchange heat. So here you have these weird curves, and this is the ideal engine right here if you can make it happen. Difficult, not impossible, but difficult. And, well, theoretically it's possible, but practically it is slightly impossible. However, the Stirling engine comes pretty close to doing this. And so the Stirling engine is considered one of the most efficient engines close to being a Carnot engine.
I know you said that it's very efficient, but it's not very powerful and doesn't produce much torque. If you built one that was big enough, could you get enough torque that it could do something useful?
Yeah, but the problem is if you build something big enough, you have to turn all those heavy parts. And it requires a huge heat differential to do it. So you're going to need like a nuclear reactor connected to it. And still, it wouldn't give you as much torque and as much power as just a regular turbine and steam system. So it becomes actually less efficient in the end, unfortunately.
Okay.
The torque is rather important.
So ultimately, cool science experiment, but not real world practical. For
Yeah,
thermal energy.
exactly. But that's true of a lot of cool science.
Sorry.
You want a break? Okay.
Those balls are incredibly resilient.
Sorry for that. We have all kinds of stuff from my STEM class kicking around the room that everybody's playing with.
Sorry about that, Mr. Daly.
Okay, here's a nuclear power plant. It is a heat engine, right? Inside here in the nuclear core, you have these rods of uranium or plutonium inside of here, and they are brought close together, and it starts a little mini chain reaction, which is a slow reaction, but it creates a lot of heat. And going through the core, you have a liquid cooling system that cools off the core but heats up the liquid. That liquid goes into a big steam generator and heats up water and generates steam up here that goes through the steam line and goes over here and creates the actual work. Right? The work is done here on the turbines, turns the generator. As that work is done, what happens to the steam?
It cools off.
it cools off because it loses energy. It's giving its energy to the turbines. The turbines get wet. The steam drips down to the bottom of this tank. They actually have an extra condenser that cools it off even further because it's really hot. So it never really gets to be liquid, even though it's cooled off going through the turbines. But they use these condensers from the cooling tower. You put cold water up into this high tower and cool off that water, and then you put this, you put that cold water down in here and cool stuff off till it's liquid and put it back through this steam system again. Notice the isolation. The nuclear power liquid core, it never mixes with the steam. It just goes in and heats the steam up with a pipe. The steam never mixes with the condenser cooling water. You've got 3 layers of protection between your extremely dangerous radioactive reactor and the cooling tower, which is spewing all kinds of steam up into the sky. Have you ever seen these things? They're just pumping steam up in the air. Now, we have 2 nuclear reactors in Nebraska. Why don't they have cooling towers? Nope, they're both active. They're both on the Missouri River. Instead of a cooling tower, they just use the river. So if you go upriver from the 2 nuclear power plants, you go north of Omaha, the temperature of the river is like 3 degrees cooler than downriver from Lincoln.
It's not harmful, it's just hot water.
It actually is harmful to the fish, believe it or not, and the plant life in the river.
Changing the temperature outside of there.
You change the temperature in their environment. And so it can cause some damage. So they actually monitor that to make sure it doesn't do too much. So again, in the winter months, you can be more efficient than in the summer months. Just like with any old heat engine. When the water is colder, it's better for the engine.
So question. If I'm, hypothetically, if I'm in China and I have the Himalayan mountains sitting on my southwest border, do I stick a bunch of nuclear reactors there and then all the power?
Melt all the snow and ice off the Himalayas? Sure, theoretically you could do that. In fact, there are a lot of power plants that are in mountains. Usually they're coal-fired power plants.
Or you could be Russian and stick it in the middle of nowhere and call it Chernobyl.
That's right.
Because that works great.
Yeah, so nuclear power plants do need a lot of cooling. They have a lot more heat in them compared to normal power plants. They create a lot more electricity. They're an extremely good source of energy and very clean.
Which one?
The nuclear power plants. There are only 2 waste products in a nuclear power plant. One of them is very small, and that's the nuclear waste. The nuclear waste you put in about, for 20 years, you put in the amount of nuclear material that you put in and take out of a reactor in 20 years is smaller than this table up here. It's not that much. It's a very small amount of material. So you have that as waste that comes out every 20 years compared to a coal plant that has mountains of waste coming out. And then the other thing is just heat. The other thing is just heat waste. It's the only 2 things that come out of a nuclear reactor besides electricity. And it creates a lot of heat, but it's just heat. You know?
The only problem with nuclear reactors is making them safe enough that they don't irradiate everybody.
Well, and the irradiation is not really the problem. That's easy to protect against. You just build a huge building that has like 40-foot concrete steel walls and you're good. The radiation is not a problem. Meltdowns are a problem.
What happens with a meltdown exactly?
So inside of this core, you have all this nuclear material that's close together so that it's almost making a bomb. But it's not close enough together that it's actually going to make a bomb. It just gets hot. And they put these control rods in between to control the reaction that slows down the neutron flux. It slows down that reaction so that it doesn't go nuclear. However, if something goes wrong and this starts heating up, for example, if your cooling system here fails and this starts heating up, it can get so hot that it'll melt through everything. It'll melt the whole reactor. It gets so hot. It'll melt every piece of metal. It'll melt the concrete. It'll melt everything and make a big slag pool in the bottom until it melts through the bottom of the reactor and starts melting through the crust of the earth. That's how hot it can get, and that's why they call it a meltdown. But if you get enough of that material all pooled together in one spot, it creates a bomb. It spontaneously combusts or spontaneously fissions into a nuclear bomb. So you would get a small nuclear explosion, essentially.
That's not good.
It wouldn't be a big one because it would happen as soon as you got to a critical mass. It would be the smallest possible explosion. But it still would not be good.
would those 40-foot thick concrete and steel walls be enough to contain that?
No,
They're melting.
no, they would be gone. It would be a pretty big bomb if it would. I mean, it would be the size of a very big conventional bomb, but it would not be big as, like, say, Hiroshima. So it would be smaller than that, but it would be a big conventional bomb. So it would probably take out a few city blocks and it would spread a lot of radiation. So yes, sir.
So how do you
Just a second. Go ahead.
Besides the meltdown, how dangerous is a nuclear power plant?
Well, the meltdown is the biggest problem. Escape of radiation, there's a lot of protection for that. But meltdowns, I mean, there's a lot of protection against meltdowns too. If a nuclear reactor overloads, essentially what they've got above this thing is a huge pool of water. And they just dump the entire pool into the reactor. They flood the whole thing. And that does two things. First of all, it cools the reactor. But second of all, water is a really good neutron inhibitor. It stops neutrons from attacking other atoms. So it will slow down or even stop the reaction. So that's one thing that they do. They have other things they have emergency control rods in between all the fuel rods that will just drop into the reactor and stop the reaction as well. So they have just safety after safety after safety. And in 50, 60 years of using nuclear power, at civil nuclear power plants, there have really only been 3 accidents.
Chernobyl, 3 Mile Island, and Fukushima?
That's right. And one of those was caused by a huge tsunami. That was inevitable. It was gonna result in catastrophe because it just destroyed everything. It was very difficult to protect against that. The only thing you could do is to build it on higher ground, and they should have in the first place, but they didn't. Chernobyl was caused by bad engineering. Their safeties were not good enough, and they knew it. They were being lazy.
Interesting.
Yeah, 3 Mile Island did not fail. It did not melt down. Their safeties stopped it. And it did not create any catastrophe, no explosion, it was a partial meltdown, but it was stopped.
So why is 3 Mile Island, like, when you said that there were only 3 nuclear catastrophes, 3 Mile Island immediately sprang to mind. So why are they famous for it then?
Because it scared the heck out of everybody. And it did shut down the reactor. The reactor is no longer active. The cooling tower doesn't do anything. It just sits there. There's one next to it that's working because they had 2 reactors on that island. I've actually flown over it before. It's kind of cool.
So they shut down the reactor that had the partial meltdown?
Yeah,
but
so
the
other one's still going just fine. They shut it down. They put a huge steel dome over the top of it to contain the radiation, and then they poured in, like, they just filled the whole building with concrete essentially, and it's just shut down for 10,000 years. In 10,000 years, we'll go back and dig it out and make some jewelry out of it or something. But until then, we gotta wait. So
Sorry, I'm asking a lot of questions.
No, it's all right.
It's off topic. If you have to implement those safety procedures to prevent the meltdown, is that basically going to end your reactor? Is that going to basically...
not necessarily, no. Many times the reactors have had to implement procedures to cool down their reactors, and that's happened many times, but it's never been catastrophic.
So you can do that, and then within a few months or years or whatever, you can restart your reactor.
Maybe a few minutes, you know.
They're really good at their job.
Yeah, they're really good at what they do, and that's what they're there for. And the computers do a lot of it. The computers are always regulating these things, so they're kept pretty safe. It is by far the type of energy that has created the least amount of death and sickness in the world, by far. There is nothing out there that has been less damaging to the environment, to people, and to everything. But we don't understand it, so we're scared of it, right? I mean, more people have died from falling windmills. I mean, come on.
We've been using wind power for thousands of years. Come on, why not the medieval knights?
That's
fought
right.
over nuclear
Holland.
power?
Okay, we're done for today. We'll finish this up next time, and then we'll start, and then we'll do our labs as well. So we'll see you guys tomorrow. You have any questions at all, Cassie, before we sign off?
If you could just email me those chapter 14 questions, that's all I got.
I will get those to you.
Okay, thank you.
No problem. We'll see you later.
Okay, see ya.